Okay, we're looking at even and odd functions. So we're going to start off with even functions. And this is from the definition on page 36 of your textbook. You can pause the video now and go take a look at that definition, or I've snapped it into our OneNote as well. It says in the definition that the exponent of each term of the equation is even. So if we look at a function where each term in the function is even, so something like x to the 6th minus 3x to the 4th plus 1x squared, and let's say that this is our function, of course, then every term you can see has an even degree. So this function should be an even function by definition. The other part of the definition is that it satisfies this property, that f of negative x is the same as f of x. What this is referring to is if we substitute a negative x into our function, the result is our original function in return. Okay, just like you're substituting in a number into our function. Well, here we are actually substituting a negative x into our function. So wherever there's an x, we're going to substitute in a negative x. So here's the placeholder for all of the x's. We're going to substitute in a negative x. And then we're going to simplify it. What this is referring to is a negative x multiplied by itself 6 times, or an even number of times, is going to result in a positive answer. Here we have a negative x multiplied by itself 4 times. Negative x times negative x times negative x times negative x is going to give us a positive result. So this result just turns into x to the 4th. And a negative x multiplied by itself twice is a positive x squared. What you can notice is that this is just our original function after substituting in negative x. So by definition, this is an even function. The third part of the definition is that the function has a mirror line that is the y-axis. The y-axis acts like a mirror line. So, in other words, it has line symmetry. An even function has line symmetry, but the line of symmetry has to be the y-axis. That's the third part of the definition. Okay. All right. Now, we're going to look at what an odd function is. And an odd function, which is on the top of the next page, page 37, says that it must satisfy these conditions. Each term of the equation has an odd exponent. So let's say we're dealing with a function g of x. We have 4x to the 5th plus 3x cubed minus 6x. Notice every term has an odd degree exponent. There's an invisible 1 here. This must be an odd function because it satisfies the definition of an odd function. The second part of this definition says that an odd function satisfies this property, that f of negative x results in the negative of the original function. Well, let's see if that holds true for our function. We have a g of x. It's saying that it satisfies f of x, but of course f and g are the same thing. It's just denoting a different function. So let's substitute in negative x in our g of x function. So wherever there's an x, we're going to substitute in a negative x. like so. And we go to simplify it. If we multiply a negative x by itself 5 times, or an odd number of times, the result is a negative answer. So it's going to result in negative x to the 5th. Likewise, multiplying a negative x 3 times, a negative x times a negative x times a negative x is a negative x cubed. This one is already simplified. When we simplify each of these terms now, we have a positive 4 multiplied by negative x to the 5th. The result is a negative 4x to the 5th. A positive 3 multiplied by negative x cubed is a negative 3x cubed. And a negative 6 times a negative x is a positive 6x. What we should notice with this answer, or this simplified answer, and our original function, well, one is just the negative of the other. And we can show that down here. We can say that if we substitute, or if we put a negative sign in front of our original function, what it looks like is this. A negative sign in front of our original function, which is 4x to the 5th plus 3x cubed minus 6x. And we simplify it, so we distribute the negative sign through each term. Inside the bracket, we should have exactly what we said we would have, the negative of that answer. Therefore, since g of negative x results in the negative of the original g of x, this function must be odd. Okay, so it fits two pieces or two parts of the actual definition. Okay, I'm going to try and slide that all up so I can use a little bit more space here. The last part of the definition is that an odd function is rotationally symmetric about the origin. We talked about rotational symmetry already. This is like a cubic function. The origin would act as the rotation point. Okay, so that this arm, if we held this point down and we spun like a spinner, this spun around, this arm would spin directly onto this arm in an angle of 180 degrees. And so therefore, this function, this particular graph that I have drawn here, is rotationally symmetric about the origin. Okay? That is unlike some of the other graphs we've had. It doesn't matter where that rotation point is. Okay? This point is said to have point symmetry, right? But does not satisfy the definition of an odd function. Okay? So this one here would not be odd, whereas this one is odd because the point symmetry is at the origin. Okay, so there's a difference there. I guess the biggest problem is when you get to a question like number 3 on page 39. We could possibly have an issue with trying to slide that all up there, but it's not working. Okay, we could have an issue with factored form. So on page 39, I'm going to look at an example like question 3b. The question is, and you've done this question already, but I didn't get you to do, well, maybe I tried to get you to do it, but determine algebraically if each function is even or odd. So g of x equals x minus 1 times x plus 3 times 1 plus x times 3x minus 1. Sorry, 3x minus 9. Okay, this is our function. We're trying to determine algebraically whether this is an even or an odd function. Okay, so by definition, we have to try and... I just need to move this stuff out of the way, and I don't know how to do that. Or I don't know how to give myself more space on the page. I guess that's the other problem. So maybe I'll just scoot that over there and push this up for now. First of all, if it's even or odd, it has to satisfy one of the conditions that g of negative x has, right? So either when we substitute in negative x into this function, the result is either going to be g of x itself again, or it's going to be negative g of x, which means it would be odd, or it doesn't satisfy either of those, and therefore it's neither odd nor even. Okay, so let's go ahead and substitute negative x in wherever there's a positive x or wherever there's an x in the equation. Okay, then we can simplify this. Nothing to simplify in the first two factors, but here we have 1 plus a negative x, so that's just 1 minus x. Here we have 3 times negative x, which is just negative 3x. And to simplify, we want to make sure, is it looking exactly like the factors above? Okay, right now it's not, but what would happen if we factored out a negative 1 from each factor? Okay, so if I factored out a negative from the first factor, I'm going to get x plus 1. If I factor a negative 1 out of this factor, for instance, I'm just dividing out a negative 1, the result is x minus 3. Factor negative 1 out of this factor, this is going to turn into a negative, this is going to turn into a positive, so if I reverse the order, it's going to look like this. Or I could have left it as 1 minus x, or sorry, negative 1 plus x. Factor negative 1 out of this term, or this factor, sorry, and it turns that bracket into a negative. The reason why I do that is because I substituted a negative x in, so I want to factor out the negative to see if it compares to each of these factors. What I notice is I have a negative 1 multiplied by a negative 1 multiplied by a negative 1 multiplied by a negative 1. I'm multiplying a negative 1 by an even number of factors. So that's going to turn into a positive 1, or basically cancels out. So the only thing that I have left is each of the factors that I've simplified already. My result is this function, and it looks nothing like the original function, that's for sure. Okay, x plus 1, I have x minus 1. X minus 3, I have x plus 3. Okay, but what I should maybe make note of is that, well, this x minus 1 maybe is just in a different order, right? This x plus 1 is the same as 1 plus x. So maybe two of my factors are, in fact, identical. But what's happening with these other two factors? So I have an x minus 3. Well, I don't have an x minus 3 up here, or do I? Maybe I have an x minus 3. Maybe I do have an x minus 3. So this x minus 3 would actually match that one. Forgetting about the 3 factor, of course. And, oh, what do I have here? I have really an x plus 3. So this x plus 3 actually does match that one. And my 3 factor is actually right there. So in essence, what I've actually done is I've satisfied the condition that g of negative x is in fact g of x. And what does that suggest about the definition? That this is in fact an even function. Now, I probably actually, by accident, picked the most difficult one out of those four. But the strategy for solving each of these even and odd functions algebraically is exactly the same. And you can see that from the examples on page 37 from example 3. There's a few examples there that will help you, particularly question C where it's already factored for you. So go back and take a look at that. Use this example as a guiding principle and then continue on with the homework that I assigned yesterday. And we'll take a brief look at it as well when I get back tomorrow.